let's take a look at an example. In this example, we are going to solve a system of linear equations algebraically. So I'm going to do this a couple of different ways. The first approach I'm going to take, this will be the only time you see it in this class, because we usually use a different approach. But I want you to see both approaches just so you are aware that there is the second approach, because sometimes we need it. And I'll explain that at the end. Okay, so let's first solve this systems of equations by substitution. So I'm going to start by just copying down my system. Now, to solve by substitution, what we want to do is we want to solve for one of the equations. We want to solve for one of the variables in one of the equations. And then we want to substitute that into the other equation. So I have some choices to make here. I have two equations, and in each one of those equations, I have two variables. I could solve for any variable in any equation. This is going to be a theme with linear systems of equations, or systems of equations generally. You often have choices. So I'm going to use this first equation here, and I'm going to solve for y. So in order to do that, I'm going to add 3x to the other side of the equation, and then divide both sides of the equation by -2. And so y is equal to -3/2 x minus 1/2. So now what I could do is I could substitute that into the other equation in my system. Okay, so we're going to put them together. And so I have my second equation in my system is 5x minus 3y. But instead of using y, I'm going to substitute in -3/2 x minus 1/2. Which I know to be equal to y based on my first equation. Remember, the idea here is that the solution of the system I'm looking for, there is an x and y that makes both equations true. So if something is true for the y in the first equation, it's also true for the y in the second equation because it is the same y. So if y is equal to -3/2 x minus 1/2, I know that from the first equation. It must also be equal to -3/2 x minus 1/2 in the second equation. And so I get 5x minus 3 times y equals 11. Okay, so I need to combine like terms. So I'm going to start by distributing the 3. So I get 5x plus 9/2 x plus 3/2 equals 11. Okay, the fractions are a little annoying, so I'm going to do a little trick here to get rid of them. I'm going to multiply both sides of the equation by my least common denominator. So that's going to give me 10x, and then when I distribute the 2 to the fractions, the 2 in the denominator will cancel with the 2 that I'm distributing. Okay, so 2 times 5x is 10x, 2 times 9/2 x is 9x, and 2 times 3/2 is 3. And on the right-hand side, 2 times 11 is 22. So I have 19x plus 3 equals 22. Now notice what we've done. Okay, and actually we did it up here. Once we plugged in, we substituted out y for -3/2 x minus 1/2. This equation that we're dealing with, now it's just one equation with one variable. And so we can solve one equation with one variable. So that's what we're doing here. We're solving the equation. So I want to know what x is. So if I keep going, subtract the 3 to the other side, 19x equals 19, which means x is 1. Okay, now notice I'm not done. A solution to a system of equations is a point that solves all the equations in the system. Since I'm in two-dimensional space, a point would be an x and a y together. I found the x, I still need to find the y. So I could substitute again, substitute into any equation that already has an x in it. I'm sorry, that has an x and a y in it. Okay, so I could plug into this equation and solve for y. I could plug into this equation and solve for y. But this one, it already has y by itself. So that might be the easiest one to use. So that's the one I'm going to plug into. So I'm going to substitute this x into this equation. So that's y equals negative 3/2 times my x, which I just found out is going to be 1, minus 1/2. So negative 3/2 times 1 minus 1/2 is negative 4/2, which is negative 2. So my x is 1, my y is 2, is negative 2. And so together, that is my solution to the system. xy equals 1, negative 2. Okay? All right, so that's method 1. Now, keep in mind, this is pretty much the nicest linear system that we're going to get in real life and in this class. We've got 2 equations, 2 unknowns. That's the smallest number that you can get for both equations and variables while still keeping it interesting. After that, you just have 1 equation with 1 unknown, right? And already it's kind of a mess. There's lots to keep track of. If you try doing method of substitution to solve larger systems of equations with, say, 3 equations and 3 unknowns, it really becomes hard to keep track of everything. Okay, so we have another method. This is the method we're generally going to use in this class. And it goes by several names. For now, I'm going to call it the elimination method. So we're going to now solve this system by elimination. So again, I'm going to start by copying the same system down. Okay, the idea here is that since I know all the equations are linear, I know that if I were to say add the equations together, I'd have some like terms, right? I have a term with a single x in it here. I have a term with a single x in it here. I have a term with a single y in it here. I have a term with a single y in it here. Okay, so I have some like terms. If I can multiply the equations by just the right numbers, I can eliminate one of the variables from the resulting equation when I add the equations together. Okay, let me show you. Right? So I need to choose a variable to eliminate. I could choose x, I could choose y. It really doesn't matter which one. I think y might be a little bit easier just because the coefficients are a little smaller in this case. But again, with systems of linear equations, we have choices. I could choose x. It might be a little harder, but mathematically, it's just as valid. Okay, so what I'm going to do, I need to get the coefficient in front of these y terms to be the same number, but with the opposite sign. That way, when I add them together after I'm done, they will when I add them together, I'll get 0. They will eliminate. Okay, the smallest number that I could get both of these to is 6, right? That's their least common multiple, 6. So I'm going to multiply the first equation by 3, both sides. In the second equation, I'm going to multiply both sides by 2. Okay, but remember, I also need them to be opposite signs. Right now, they'd both be negative, so I just need one of these to be negative. So I'll multiply by negative 3. I can draw it in so that it... There we go, close enough. So my 2 equations become 9x plus 6y equals negative 3. That's what my first equation became. My second equation becomes 10x minus 6y equals 22. Okay? So notice I didn't really change the system at all. I just made the equations look a little different, right? You could always multiply both sides of an equation by the same thing. It's still the same equation when you're done, it's just numbers are a little bigger, right? But now, look, I've got a 6y in my first equation, I've got a negative 6y in my second equation, and it's the same y, right? Same x, same y in both equations. So what I could do is I could add the equations together. So if I add the equations, 9x plus 10x is 19x. And then 6y minus 6y, they go away, they eliminate. And on the right-hand side, negative 3 plus 22 is 19. And now I have one equation with one unknown, which means x is going to be 1. Okay? Now I still need to plug in to find the y. I could plug into any equation with a y in it. In this case, let's plug into that very first equation just because we have smaller numbers there. Because I still need to find that y. So I have negative 3 times x, which I just found is 1, minus 2y has to be equal to 1 to make this system of equations true. So I get negative 3 minus 2y equals 1. Add the 3 to the other side. Negative 2y equals 4, or y equals negative 2. And so I get the same solution as before. X equals 1, y equals negative 2. Okay, same method both ways. But this way, our method by elimination, it was a fair bit faster, right? Just looking at them side by side, you could see that the side on the right is shorter. And what's more, we were able to manipulate things so that we didn't have to deal with any fractions like we did on the left-hand side. Fractions were a little bit annoying when we were solving by substitution. Okay? Elimination does tend to be the easier method. And so we're going to be using elimination almost exclusively in this class. And we're going to actually formalize it a little bit to make it a little more useful to us. So why did I even show you the method of substitution if it's longer and harder? Solving systems by elimination, it only works for linear systems of equations. If you have a nonlinear system of equations, then this method won't work. Instead, you would have to use this method. This is our go-to method for general systems of equations. General method to solve all kinds of systems. If you're going to do it algebraically, this is your best bet for solving a nonlinear system of equations. Now, of course, this course is linear algebra, so this is going to be the method that we are going to use for this course.